With these fundamentals in mind, we can consider the effects of various dimensions and proportions in the design of centrifugal fans. After doing so, some of the formulas used in their design will be easily understood and applied. The effect of wheel diameter and speed. Because velocity and pressure are the most easily determined factors in fan behavior, yes, those are the easiest ones. We rely heavily upon them in design and testing. The diameter of the wheel, or rotor, and its speed affects both factors. Since the air is expelled at the periphery or outer edge of the wheel, it will have attained the velocity or speed of that surface as it is thrown off by centrifugal force. So I guess that's where we get the term centrifugal fan. It's from the centrifugal force. To determine air velocity, it is only necessary to know the speed of the wheel's outer edge. The velocity of air increases directly with an increase of wheel diameter. Doubling the wheel diameter will double the velocity of air delivered if the wheel speed remains the same. That's good to know. The circumference, perimeter, or periphery of a wheel is found by multiplying its diameter by 3.1416, which is pi. That number 3.1416 is pi. Oh, no, not like fruit pie. It's like a mathematical pi. Yeah, I know it's confusing, but it'll all come together. I mean, I'm learning too. It's for both of us. For example, a 10-inch diameter wheel will have a circumference of 31.416, which is 10 inches times 3.1416, which equals 31.416. A point on its perimeter will travel 2.618 feet. 31.416 divided by 12 inches per foot equals 2.618 feet. In each revolution of the wheel, if the wheel is driven directly by a motor that runs at 1,725 RPM, which stands for revolutions per minute, then its peripheral velocity will be 4,516.05 feet per minute. Because 2.618 feet per revolution times 1,725 revolutions per minute equals 4,516.05 feet per minute. Thus, the theoretical velocity of the air thrown off will be 4,516.05 feet per minute. In practice, air velocity will diminish as it travels away from the wheel. Total output is affected not only the distance traveled, but by friction, slippage, and other less obvious factors. These can all be taken into account with the coefficient of discharge factor, which is usually 0.8 in ordinary work. In other words, you only get about 80% of the output predicted by the formulas. The effect of air velocity. When air is moved by force, it will displace or push other air out of its way. Moving air exerts pressure in the direction of its travel, called dynamic pressure. If resistance to airflow is encountered, pressure builds up until the maximum capacity of the fan is reached. Such pressure, called static pressure, is exerted equally in all directions. If the entire output of the fan is confined to a tank, chamber, or other pressure vessel, the total pressure measured will be static pressure. Since the air is not moving, there is no dynamic pressure. If a part of the air is allowed to escape from the chamber, the static pressure will drop. Since air is now moving again, the system now exhibits dynamic pressure. You might think that dynamic pressure will increase by exactly the same amount that the static pressure decreased. Not so. In practice, the moving air must fight its way through the static pressure before it can escape into the rest of the system. The dynamic pressure of the moving air will be reduced by static pressure that resists its flow. The remaining dynamic pressure is called the velocity pressure. This is the practical working pressure that delivers the stream of moving air. The diagrams below illustrate the effect of dynamic, static, and velocity pressure in a fan system. The relationship between the velocity of airflow and its velocity pressure is accurately predicted by the formula V, which stands for the velocity of flow in feet per second, is equal to 66 times the square root of h. And h is the velocity pressure in which the velocity pressure in inches of water column. As air is assumed to be dry at 60 degrees Fahrenheit. The formula may be transposed to find any factor when the other two are known. The formula in the last instance, which is this one I just described, sorry, I didn't show you what the formulas look like. See, I know it's hard to see there. V equals 66 times the square root of h. Yeah, you just need to see a little clearer there. How about this one? Yeah, there's the other formula. This is the one that they're talking about that was transposed here. Oh goodness. Here you go. There you go. There you go. The formula may be transposed to find any factors when the other two are known. V divided by 66 equals the square root of h, which is the last instance. In the last instance states that the velocity in feet per second divided by 66 is equal to the square root of the velocity pressure in inches of water column. We can apply this formula to our 10-inch wheel at 1,725 RPM to determine what pressure it will produce. That's interesting. H equals the velocity divided by 66 squared. So it's really H equals velocity over 66 times velocity over 66. So let me just show you this formula. See, here's what the formula looks like if you were wondering. That's what the mathematical formula looks like. And then here's a little indication. Here's a picture of a dynamic pressure, static pressure, and velocity pressure. Can you see that okay? Yeah. I know it's just we probably want something with colors, but a lot of these boring technical manuals don't have a lot of colors, I'm sorry. We'll get some better books. For you, anyhow. I like this stuff. This is what Grandpa likes to do in his free time, and I know it's boring, but I'm a grandpa, so it's okay. I can be boring. We have already calculated that the theoretical velocity of the 10-inch wheel at 1,725 RPM is 4,516.0 feet per minute. The decimal fraction is insignificant. The value can be rounded to 4,516 feet per minute, since the formula calls for velocity in feet per second. 4,516 feet per minute divided by 60 seconds per minute equals 75.27 feet per second. Dividing this by 66 gives us 1.14. If we square this, we get 1.3 inches of water column pressure. Now, the way they did this is they have a whole series of formulas that show how everything was worked out. Velocity is velocity in feet per minute equals velocity feet per second divided by 60 seconds in a minute. 4,516 feet per second divided by 60 seconds in a minute equals 75.27 feet per minute. And the h equals velocity divided by 66 times velocity divided by 66. So that's 75 divided by 75.27 divided by 66 times 75.27 divided by 66. And that equals 1 point. Oh, do you disagree? Check H? Oh, H. Remember, H equals... H is the velocity pressure in inches of water column when the air is assumed to be dry at 60 degrees Fahrenheit. That's what that H was. I'm sorry if I kind of like threw a bunch of info at you all at once. So it equals 1.14 times 1.14, which equals 1.3 inches of water column pressure. This can be verified by using the other two variations of the formula to see if the numbers calculate out correctly. So they go through all of the calculations here. In another instance, a fan capable of delivering air at a velocity pressure of 4 inches WC, which is water column, I guess they're abbreviating it now, might be required. The formula is applied to calculate the velocity of flow from the pressure. Since motor speeds are stated in revolutions per minute and velocity must be in feet per minute, we must multiply 60 seconds per minute, 132 feet per second, times 60 seconds per minute, which equals 7,920 feet per minute. If a 1,725 RPM motor were to drive a fan directly, a peripheral velocity of 4.59 feet per revolution of the wheel would be required to deliver at 4 inches of water column pressure. Obviously, the 4.59 feet is the distance around the wheel or circumference. Oh, I hear it. Are you fighting one out? I know. You can push one out. I will just change you again. Obviously, from this we know that 17.5-inch wheel running at 1,725 RPM should deliver air at 4 inches water column pressure. Of course, a smaller wheel running at higher speeds gives the same results, and so does a larger wheel running at a lower speed. These combinations can be investigated by running numbers through the formula. The effect of wheel width. That's an interesting one. Fans are rated according to their ability to move a quantity of air against resistance. Ratings are usually given in cubic feet per minute against a value of static pressure in inches of water column. The theoretical capacity of a fan is the product of the velocity of flow in feet per minute multiplied by the area of the discharge times the coefficient of discharge, which has been given as 0.8, because they're only about 80% efficient, apparently. The theoretical discharge opening is called the blast area. Well, that sounds exciting. And is calculated by multiplying the diameter of the wheel by its width and dividing the product by a factor that varies from 2.5 to 3 in practice. Since the larger value allows the greatest margin for error, it is the safest to use in casual design. The formula to find a blast area is area equals D times W divided by 3. A blast area, A is the blast area in square inches, D is the wheel diameter in inches, and W is the width of the wheel in inches. What? Or do you want to see? Do you want to see it? Here's the formulas. That's what all the formulas look like in there. Yeah. Oh, squirt one out. Oh. Oh, pushing. Do you need to change it? Do you want to change it, or you need to squirt out some more? Squirting out some more. Oh. think you're pushing out of poop. Okay, we'll continue with our video coverage of how to design and build centrifugal fans after I change this diaper.